You're good to go.
Yes. Okay. Good. Great. Thank you.
I'll do a quick intro that.
Or not, that'd be fine too. So yeah.
Hi, everyone. Welcome to the seminar. I see there are a lot of people online, more than 30 people online, which is great. It's very nice to have Scott back in our seminar. Scott Emerson is Professor Emeritus in UW Biostatistics. His educational background is very interesting, includes bachelor's degree in physics, master's degree in computer science, and MD, and all from the University of Virginia. And he completed his PhD in biostats at this department in 1988. And he was faculty at this department between 1995 and 2017. And Scott has deep expertise in clinical trials and has been part of advisory committees for the FDA. And last time in 2022, Scott was back giving a very exciting seminar about advisory board experience for the Alzheimer's disease drug. And it's very exciting that you're back today and talking about exciting topics. Thank you.
Great. Well, thank you. I enjoy the opportunity to give this seminar. I just should, since I am talking about things that I have been paid for by the pharmaceutical industry, just point out that I was paid to be on the steering committee. That is all over. They don't pay me to write papers, but they did pay me to on that. So no way am I trying to recommend particular treatments. I want to talk about statistics here. The statistician should be a paid skeptic. While I do have the medical degree, first of all, I did nothing clinical thereafter. So I would point out to everyone that I know as much obstetrics as any orthopedic surgeon. And so that's about the extent of my knowledge. I also always point out that while I'm a paid skeptic, I provide my cynicism for free. And so it's my abstract. I just put it there so that I know where it is when I want to go back to it. My perspective, since 1985, the target of my statistical methodologic research has been distribution-free adaptive causal inference, both brief with distant Bayesian and the presence of missing data. Sounds pretty good by modern buzzwords. Let's see what I really mean by those buzzwords. And that is causal inference. Well, I work in randomized clinical trials, and you just can't get more causal than that. I like it to be distribution-free, based on the central limit theorem. I do frequentist inference that provides credible Bayesian inference. Adaptive clinical trials using, well, you know, we do phase 2 trials one way, we look at the results and we change it and we do a phase 3 clinical trial. And that's adaptive. I've looked a little bit of adapting in the middle of a clinical trial too. And then missing data. Well, I've always been interested in survival data, just, you know, Kaplan-Meier estimates and proportional hazard regression, and that's missing data. I have in applications also looked at multiply imputed longitudinal data, looking at competing risks and things like that. But, you know, I give all the modern statistics buzzwords, but I always like to point out that when I was in 3rd grade, this was modern architecture. And so you have to remember that every time anybody uses the word modern, there's nothing so old as 1960s modern. And so I'm always nervous about that. And then I also like to quote my mother, who for some reason, you know, she had 7 kids between 1950 and 1959. And for some reason, she had to regularly quote this to us. And then a disclaimer, you know, you get what you pay for. I'm retired, so you're getting what a retiree does. But again, quoting my mother, who would say, if you're lucky, you get what you paid for, but you sure as hell aren't going to get anything that you don't pay for. And that has 2 things. One is the questionable value to you of the seminar. And so you can say, but I paid with an hour off my life for it. And well, yeah, that won't get you very far. But the other thing is the clinical trials. And the clinical trials themselves are extremely, extremely expensive, as I'll talk a little bit later. So the topic for today is this statistical collaboration on these large clinical trials. The design, the conduct, and analysis, going to talk a little bit about that. The reporting. I think that's just a very important part that we sometimes give short shrift to. And then after that, it's the lather, rinse, and repeat of your shampoo bottle. Yes, you design, you conduct, you analyze, you report, you explore it again, you form a new hypothesis, you do it all again. So I'm going to use the setting of these cardiovascular outcome trials. And when I first got involved with them quite some time ago, was actually with insulin. And so this was insulin. Did they get better control of diabetes with this insulin? And yes, but now there was this concern, but do you know you're not making heart attacks worse? And so they had to do a cardiovascular outcome trial there. And then this is the same sort of thing. So be working in an area that before we did these trials, we were quite confident that the drug benefited glucose levels and it also benefited weight. But now the question is, all those things that are associated with hyperglycemia or obesity, has it impacted that in a beneficial way? And initially, the question is, make sure it doesn't impact it in a harmful way. So I'm really going to talk primarily about obesity. I'm only going to talk about diabetes because this was a diabetes drug repurposed to obesity. So goal of a clinical trial, we want scientifically rigorous, statistically precise determination of whether a drug is efficacious, safe, and by the combination of them, we call that effective. And then quantification of those effects, that also matters. We want to explore secondary outcomes. We want to explore subgroups having greatest effects. Quite a few years ago, it was all the rage in modern statistics and modern biostatistics to talk about personalized medicine. And my complaint all the time was, from day one of medical school, we talked about personalized medicine. We treated people who were pregnant different from people who had a broken leg, different from people who had cancer. And that's just personalized medicine. What we're constantly trying to do is refine our definition of disease and refine our definition of treatment to have them match up as best as possible. But we've always done that. So we also want to understand these potential mechanisms of action. Bottom line, do we care it works? But the next thing is, but the next drug, how should we design the next drug and what will it be acting on? And that's a big deal with this particular drug because frankly, we don't know how it works. Other drugs that we don't really know how to work include all the statins that if you talk to some people, we should be putting in the drinking water. So, we don't truly know exactly how we're getting the benefit from it, even when we do know we're getting a benefit from it. We want this to be in a cost-effective manner. You do a little bit of multiplying here. The per patient cost of one of these clinical trials is around $50,000. Okay, we have 17,000 patients in one of the clinical trials, 9,600 in another, and these are just two of the myriad of clinical trials they've done. But this clinical trial itself, by these measures, is costing close to $1 billion. So back in the days when statistical genetics was new and people would come in and say, well, I've got these 10 data points. I go, why only 10? Well, you don't realize it costs $1,000 to do one of these microarrays. And I said, so, it's way more than that to do a clinical trial. So the selected issues I want to talk about are just things, as I said in the abstract, these are just sort of the perspectives that as I looked at doing all of this and looking at the planning of this and what questions want to be answered and the secondary analyses, lots of issues that, I was constantly coming up against the medical literature, a lot of what I wanted to know and what they instead told me. And then the different things that we might want to look at to try to answer these questions. So this is composite endpoints, time to event analyses, control of the type 1 error across multiple endpoints, sequential sampling plans, handling missing data and competing risks, subgroup analyses, quantification of the joint distribution of continuous and time to event endpoints, exploration of mechanisms of action, and adherence-based analyses. Okay, so now all of these things, I have to tell you, it's not something brand new that I'm using to address this. Common sense, well, possibly Tom regularly gives us statement that common sense isn't very common. So maybe that is brand new, but a lot of it is really looking at how we would use standard techniques to really address these questions. Need to talk a lot about estimates. And this is the question of what is it that we're trying to estimate? What is it that our goal of our clinical trial is? And so the indication, which to me has four things. It's the disease, the population, the treatment, and the outcome. You change one of those, you've got a new indication. And again, for this drug, started off as diabetes, and the indication was to treat hyperglycemia. We're now into the world that is getting an indication of to prevent heart disease, and prevent heart disease in secondary prevention, to prevent it in people who've already had a heart attack and who are either obese or have type 2 diabetes. But again, that's a different. We want to talk about what's the clinical importance of the distributional summary measure. Are we just interested in a mean effect, or are we interested in how many people we get below a threshold? So in hyperglycemia, for instance, is it enough just to lower the glucose in somebody with diabetes, or do we want to get them back down to the normal level? Well, this is the difference between looking at a mean and looking at a binary proportion, right? And again, that's a clinical question at times, and the clinical importance of stratification. And again, that's this idea of who are you comparing to whom, and what's your patient population care about? Of course, statistically, we also care about summarizing the outcome distribution, where the mean, the geometric mean, median of continuous data, proportion or odds above a threshold, time average, hazard ratio. And I used to ask students when I'd be teaching the applied statistics, and I go, well, how should we summarize this data? What do you do? And they go, it's censored data. You have to use proportional hazards. You do not. You don't have to use it. The fact is we do. And so why is that? And where does that get us? And where does it hurt us? And so on. Covariate adjustment that gives us precision in a clinical trial. We're not trying to get rid of confounding with this. We're trying to get precision. One statistician's mean is another statistician's variance. In an observational study, yes, we're trying to take the bias of the mean. In a randomized clinical trial, it's all precision. And then doing per randomization analyses, because that's what's giving us the causal effects. So in a cardiovascular outcome trial, what are we interested in cardiovascular disease? Well, I ranked them in an unusual way here. I ranked them in the endpoints that I'm sure we're interested in, down to the ones that we have to live with. Okay, so to me, almost everybody would rather live a while longer. And the remark about Alzheimer's is there's some Alzheimer's patients that you went into and say, your mental function will be better for 3 years and you'll die the day after. Well, do you want this treatment? And many would say yes. So there are qualifications on this, but all-cause mortality. However, under the it's not my job category, the cardiologists will say, yeah, but we're treating cardiovascular disease. So can we see what we're doing for cardiovascular disease and not deal with the nuisance of whether you die from cancer, whether you die from an airplane accident, whether you die from other accidents? And I'll tell you that in cardiovascular disease, we have a greater propensity to think we're going to impact all-cause mortality than in a cancer clinical trial, that they will say, we're trying to cure the cancer, and most people will die of cardiovascular disease, and we're not trying to do that. So again, this comes there. But in cardiovascular disease, for those of you who don't know, it's not real easy always to diagnose when somebody has died from cardiovascular disease. When I came through medical school, you said, if somebody died within 24 hours of their coming to the ER, you couldn't tell whether it was a heart attack or not, because of all of our diagnostic methods required somebody to live for 24 hours before we could use them. Well, now we're a little bit better than that, but not perfect. And we still have people who die suddenly with no other obvious cause. And in the cardiac world, we count that as cardiovascular death, even though we still split it out. We knew this was a cardiovascular death, or we have no other explanation. So it's just this unknown death. And then we come to the endpoint that's really used most often, is this major adverse cardiovascular events, so MACE, and I'll just refer to it as MACE from here on out. Myocardial infarction, okay, and then I put in here unstable angina. That was certainly a diagnosis when I came through medical school, although on a call recently, somebody goes, aren't we always calling this heart attacks now that we have troponins to measure? And so again, this diagnosis changes. Stroke, ischemic versus hemorrhagic, but particularly for ischemic stroke, when I came through, we had transient ischemic attacks. Now we treat somebody so quickly that we can't tell whether it would have resolved by itself within 24 hours, which is what the TIA was, or whether it was going to be a stroke. And so that sort of has been now folded into the stroke. And of course, we're back to that death from cardiovascular causes, which again, will include the sudden death. Heart failure composite, hospitalization or urgent treatment for heart failure. And again, tying that in, somebody who's dying from cardiovascular causes, what should we do with that? Well, then we always fold it into this endpoint as well. And then you come down to things that I'm not talking about today, but peripheral vascular disease, the same things that clogging up your coronary arteries and your cerebral arteries are clogging up your feet arteries, and they can lead to these major adverse limb events and adverse renal outcomes. These are all tied together on these various studies. We look at those endpoints too. I'm not talking about that. Yes, sir.
Every one of these endpoints, frankly, is feels function survives.
Absolutely.
None of them are biomarkers. Although the renal division of FDA does accept EGFR.
Yeah, that EGFR is an endpoint there. And that's something that I talk a lot about in some of the economic things, as we're saying, you're lumping, there's a big distinction in medicine, although they don't always make it out. A clinical event versus a subclinical event. And every now and again, we promote something that was a subclinical event up to something that we'll call clinical because we look at it close enough. Hypertension is one of those. Hypertension used to just be a subclinical event, a silent disease. Now you can get an indication to treat hypertension, but it used to be only if you were making an impact on a true clinical endpoint. But the clinical endpoints that do, the feels function survives is the major aspect that we're looking for. And again, on this hospitalization or urgent treatment for heart failure, that's a little bit softer because by the time you're doing a study with 17,000 people, they're coming from all over the world. And the definition of hospitalization in the United States is different from hospitalization in Germany, is different from hospitalization in Peru, and so on. And so you have to worry about that. Okay, we're interested in what are the scientific efficacy and safety estimates. And the first thing that we answer, because this we can answer, is what's the effect in the population. And our goal is to do an analysis that identifies a population as close to an individual as possible. But, we don't always succeed at that. And so we're going to go with the intent to treat. I do not like the term intent to treat because so many physicians will tell you, but I want to know not just the idea that I considered treating the patient, but if I treat them, what will happen? And I have sympathy for that. Our definition of intent to treat, or mine, is really per randomization. I'm doing this for statistical and scientific rigor. Rather than that, I do sometimes wonder, for instance, you can take a treatment and say, I want the true intent to treat. I'm going to try you on a new drug. And then you get a headache from it and you quit taking it. Okay, that's one time. I want to know how safe you are from that. But then I also want to know the person who's going to take it for 50 years, what happens to them? And so I changed these things. I tell people regularly on calls these days that I'm going to lose my statistician union card because I'm pushing for a bunch of per protocol analyses because I think these are important questions just for hypothesis generation, just to be able to understand that. So I'm going to talk a little bit more about these, but we have to be very, very careful because while it's an interesting basic science question, can be used to explore mechanism of action, it might be useful to try to describe prognosis. But as I will point out a little later, you can definitely go wrong by not having a randomized comparison group, a concurrent group. So now, where did we start off? What do we know prior knowledge? You're going to see a lot of these tables that are just existence proofs. I'm not expecting you to read them. I'm just saying this is what we already knew. And what this is this was published in 2021, but all of those studies that are listed are studies of a glucose-like peptide 1 receptor agonist. And I'm going to be talking about one such drug, semaglutide. But we have lots of data on drugs within this class, and there's been steady improvement over time by manipulating the molecules a little bit. But they can do a meta-analysis. And all of these are the point estimate plus a confidence interval for these different studies. The cardiologists, all I need to do is mention the name, and they'll tell me what every endpoint in the trial was. I have to look them all up at all times. But you can see that for what it's worth, Sustain 6, Pioneer 6, and then Select and Sol were all with semaglutide. Leader was with liraglutide, which was an earlier generation drug. And I'll be talking a little bit more about the Excel study, which is exenatide later. But they're all the same class of drugs, and they were looking at the MACE, cardiovascular death, and then they separated out. They just myocardial infarction or just stroke rather than train them together. So that's what we knew about the cardiovascular outcomes already. We aren't, clearly not having to prove that. SOUL, which I'm not going to talk much more about because it's just finished and all we have is the press release on that. But for what it's worth, it was looking at the same thing, but it was oral rather than a subcutaneous shot. And so it was looking at a different administration. Okay, what about weight loss? Well, we already knew that. And in fact, in 2014, FDA approved liraglutide, which was an early generation GLP-1RA, just for weight loss, and this was just more or less a serendipitous discovery. Most diabetes treatments we're hoping will cause weight loss, but it was pretty profound weight loss with liraglutide. It's more difficulty, but they knew you could lose weight, but when you look up the label for it that the FDA granted back then, you will find them talking about the weight loss that you get. They'll also talk about, it lowers your cholesterol a little bit, it lowers your blood pressure a little bit, but they had no data on whether that improved the bad effects of obesity, which I liked this figure that I just found recently, but it shows all of the diseases that are associated with obesity. You name an organ system, it's associated with that. So we think about the heart and brain a lot, but cancer is tied in there, kidney failure, joint pain, all of these things are tied into obesity. And these drugs were approved for weight loss without knowing whether it really made any impact on any of this. Of course, in the United States, obesity, these are the European and North American countries, and you see that we're winning this race by far. So all of that disease, this is a major interest to the public health of the United States. So the SELECT trial design, the key point here was we were trying to look at obesity in the absence of diabetes. So patients could get into this clinical trial if they were obese, and we used a BMI of 27, which is actually, if I want to please the people who work in this area, I'll say overweight or obese. Obese is 30 and above, overweight is 27 to 30. And they all, because we needed events, right? And so they went after this secondary prevention, people who'd already had a heart attack, a stroke, or peripheral vascular disease. But truly, that was more just to get it so that it was 17,000 patients instead of 170,000 patients to get the number of events. And the rest of them, it's there. 804 sites in 41 countries in Africa, Asia, Oceania, Europe, North and South America. Apparently we did miss Antarctica, but that's it. Semaglutide is administered as a shot once a week. Yes. By the way, I don't have to get through any of this talk if you have questions. So
I found it interesting how you described why they included people with prior CBD. And I wondered, why did they choose overweight and obese rather than just obese? Because it seems like obese, you might get more events, but if you have a lower BMI, maybe they can market it to more people.
yeah, it's a really interesting question. I mean, when you've looked at observational data with obesity and overweight, I used to, when I taught, the 514, 517 class all the time, a favorite data set of mine came from the cardiovascular health study. And in that, you found a linear trend towards better survival the heavier you were and the higher your cholesterol was. It was a sort of a U-shaped trend, but if you tried to prove it was a U-shaped trend, you couldn't do it. Now, how much data you have? But again, so that's this thing of saying, where is the step? Because there's clearly a step, but is there really that much of a difference whether you're 27 to 30 or not? And then also, the prevention, should you wait till just before somebody's in really bad shape, or should you try to prevent it there? But it was probably sample size, I'll say. It's not unusual that we do it there. In this, there are adverse experiences that go with this. Some patients do not like this drug. It gives them GI upset. And so they have found over time that if you ramp it up slowly, then you don't have it. It becomes more tolerable. Okay. And if you're going to ramp up the drug slowly, then you also need to ramp up placebo slowly, just to maintain the blind. Okay, so when you're doing a clinical trial, you need to choose a primary endpoint. And so much of it's tied. I'm going to talk all about the regulatory world. NIH does studies that's not regulatory, but let's talk about where the money is, right? And so you want to get this drug approved, and the FDA very much wants to see a primary endpoint, and it wants you to test at a one-sided 0.025 because the law calls for 2 studies. Actually, it doesn't call for 2 studies. It calls for studies, and 2 is the smallest number that allows you to use plural. So it calls for that. But the FDA has relented a little bit, and for no particularly good reason, and that 0.005 is not carved in stone, but they will accept 1 study if everything is aligning and you hit 0.005. So that we call a pivotal study. But then they also look for key secondary endpoints. And some of these are geared towards what can we get into the package insert. And so we want to claim that, yes, this makes you lose weight, but we also want to say it improves your blood pressure. Well, then you better be able to show that it has also improved your blood pressure. So they will be looking for this. And it might even make it into the indication, or it might only be printed in the package insert. And why does this matter? Because if you want to advertise your drug, you can only advertise it for the things that the FDA has said you can advertise it for. As with most rules like that, it's violated regularly. I was an expert witness in a study where, not a study, but in a case where actually the CEO of the company did go to jail because they were pushing off-label uses too much. Secondary analyses. Here's the supportive and the secondary. Alternative summarization of the major outcomes, alternative ways to look at it, just to be sure it's not a type 1 error, or be more sure it's not a type 1 error. Supportive clinical and subclinical outcomes, and of course, exploratory subgroups. So the select clinical trial endpoints, the primary endpoint was MACE. The confirmatory was death from cardiovascular causes, the composite heart failure endpoint, and then death from any cause. Other things that they could have considered was looking at stroke by itself, for instance. That would be a different indication. They could look for renal effects. They could look for limb effects and so on like that, but they went with the 4 of them. But they had other secondary endpoints that they didn't control the type 1 error on, the multiplicity. So expanded outcomes and individual components, the kidney endpoint, and progression to diabetes or pre-diabetes. Again, here we were doing something that was just the obesity. Now, in the planning of this, I kept saying every time that they started going, and now some of these patients will progress to diabetes, and I would give the example every single time. And so Pavlovian, they started saying, oh, not that example again. I said, yes. And I can show that if you start newborn babies on oral contraceptives, I prevent pregnancy. But the key point is you don't want to start them that early, you know? And so in this thing, it was saying, if the only way that we're going to improve on in the obesity is treated in the people who eventually develop diabetes, then we should be doing a different clinical trial. We should test immediately giving semaglutide versus waiting until you get the diagnosis. That would be testing that question. We wanted to stay with obesity. So time to event endpoints, truly, we have a binary endpoint, right? The binary endpoint is you got MACE or you didn't. But not everybody's going to have MACE. We got to allow for time somehow. So we'll look at the time till they get that. Alternatives would be look at the proportion that they had after 2 years, but it's not quite as powerful analysis as being able to use all of the data if you feel using all of the data would give you the same answer. So we do that. So this administrative censoring is what we feel most comfortable with. Maybe we shouldn't always, but we do feel comfortable with that because we like to pretend it's non-informative. But when we use the Kaplan-Meier estimate or the Cox proportional hazards, this is exactly equivalent to assuming the data is missing at random. Exactly. I'll talk about this again more with the missing data, but suffice it to say, people do sensitivity analyses for these that they just use the exact same missing at random mechanism. Exact same thing. I go, of course it shows the same thing. It's the same analysis. In this case, the statistical information is the number of events, not the number of subjects. Now, if you really believe in proportional hazards, and you know that you need 500 events to have this precision, it does not matter whether you take 500 people and follow them until they all die, or you take 8 billion people and follow them for 15 seconds until 500 of them die, and they'll answer the same questions. And the fact that you think that's ludicrous is, of course, the reason why proportional hazards doesn't always obtain, but sometimes it's reasonable. But we're worried about conformative censoring. This is all the news that fits. I did write out lost to follow up in one place, but it didn't fit on the line anymore. So I just used this common thing of just people who were on your clinical trial and you couldn't find them anymore. So lost to follow up. And then competing risks. And so this is something that, you know, again, we're interested in people who die from cardiovascular disease, but if they're hit by a car, we can't observe. You know, veterinarians have the advantage of cats can die 9 times. So after they die the first time, we can see what happens to them their next death. But we can't do it with people. I have worked on cat clinical trials. Multiple endpoints, we have to control the type 1 error. This is something that is a frequentist problem, truly, not a Bayesian problem, except for we're all frequentists when it comes to looking at multiple endpoints. And so the fact is the probability of A or B is always at least as great as the probability of A. That's, you know, this basic probability, and we have to live with that. So frequentist inference holds sway, full pre-specification. A p-value has no meaning unless you had the question before you had the p-value. If you have the p-value first, it's, you know, a number. I can control, and this is the other thing, is I can control the type 1 error without ever looking at the data, right? I can generate a random number, and if it's less than 0.05, I tell you that's the p-value, and that's it. So this is the silliness of frequentist inference on its own. But Neyman Pearson says, you got to consider power and the type 1 error at the same time. And it also says you have to have pre-specification to make certain it's really a p-value. And then I'll tell you that I can get approximate Bayesian inference in a designed experiment just from knowing the sampling distribution. And so we do that. However, if I give you my frequentist probabilities, you can do a very close Bayesian analysis with your own prior. If you do your own Bayesian analysis and give it to me, it's completely useless because I can't get back to what my prior was. So in some respects, the sufficient statistic for Bayesian analysis is the p-value in power, or actually it's the entire power curve. What are the most common methods we have for controlling type 1 error? Well, if you have co-primary output endpoints, we use Bonferroni. You split it across them, right? But when we have multiple secondary endpoints, nowadays they have really honed in on this idea of hierarchically. Answer the first question first. If that's positive, now you can go to the second question. If that's positive, you can go to the third question and so on. And that's way easier to think about than all of the multiple comparison procedures I learned with ANOVA back in my youth. The FDA, if you're going to use sequential testing, they did force us. And this is something we went around with them on this, as I said, can't we just estimate the correlation between the primary and secondary endpoint? And we showed them how you would be able to tell if you were getting into troubles. And they said, we don't want to have to look. And so they said, you have to put a group sequential stopping rule for your secondary endpoints too. Now, how do you choose this hierarchy? Do you choose it according to what's most important from a regulatory standpoint? Or do you choose it on the plausibility that you can demonstrate it? Well, if you know you're going to be able to demonstrate it, and this is often the case, for instance, we could put weight anywhere in there because we know the treatment is going to change weight. Who even cares, you know? But as we come to this cardiovascular outcome, the MACE, then CV death, then the heart failure, then all-cause mortality, what order should we put them in? And there was actually some suggestion, if you look through all of the meta-analyses, that all-cause mortality wasn't that bad a thing to try for. You might not get it, you might. But the one thing that comes down to it is the FDA will never, ever, ever give you an indication of this drug is to be taken to prevent death. It always has to be death for some reason. And so, again, cardiovascular death should be higher than that on those grounds, even though the plausibility is there. So the statistical analyses, I highlight a couple things on this. You know, it was how many endpoint events we were going to have. They had 90% power. You need to have high power. What was the alternative? One side level 0.025. The interim analysis had to be specified, but way down at the bottom over here, multiple imputation for missing values under a missing at random assumption without adjustment for multiplicity. Okay, missing at random assumption. How many different missing at random assumptions are there in the world, right? It's uncountable. So just specifying that tells us next to nothing. And I can't tell you, you know, obviously we gave more on the paper and things like that, but the clinical world will accept you saying the word, well, we use missing at random, and they don't totally understand the difference between missing at random, missing completely at random, missing not at random, and they don't care. I said I was doing something. So, you know, just saying that was all that was specified. These slides, by the way, when it's like this, they're coming from the talk that was given at the AHA. So these come from me. What happened during the conduct of the study? COVID showed up, right? And, you know, worried us from everything. Logistics, how are we going to get the drugs to people? How are they going to come in for their clinic visits? And I basically said, you know, a lot of this stuff, they come in for their weight things. Who cares as much? But we do want to find out if they've had an event. That's what really matters. We do want them to get their drug as much as possible, but the rest of the stuff we can have. But then COVID, how does it kill you? You know, I monitored some clinical trials and they said, well, if somebody dies, how will we know if they died from COVID? I said, well, maybe if they fell and broke their neck, I'd say that would be the one thing that I couldn't ascribe to COVID unless it made them dizzy is why they fell. I mean, you know, everything else COVID was affecting, you know, and just you couldn't say that. So we were worried about the impact it would have on event rates, and maybe they would be balanced. Maybe the treatment didn't do anything, but maybe the treatment did do something. I mean, maybe particularly if it was having a cardiovascular effect, and about half of COVID deaths are really cardiovascular more than they're respiratory. We didn't know, but we had to pre-specify what we were going to do, and also with the adjudicators know how to do this. I worked on several DSMBs at this time. Sometimes it was respiratory people, and they all presumed that COVID was just a respiratory disease. Sometimes it was cardiologists, and they all presumed it was just a cardiovascular disease. So, it's a difficult thing there. And then we come to, you've done the clinical trial and you're reporting the results. And here's where I really want to talk about what would make my life easier is if everybody reported the data that I wanted to see when I wanted to compare across studies. So table 1, the baseline data. Why do we do that? Why do we do descriptive statistics? I teach that there are 5 reasons why we do descriptive statistics. And one of the first ones, well, it's number 2 actually, is just materials and methods. Which patients did we get? And number 3 is what assumptions are we making? And one of those assumptions is equivalence between the groups, okay? I don't care at all about technical statistical assumptions. I just don't care about them. But confounding type issues. And when we look at balance between the treatment arms, means, and you can all go home and show me the distribution, I only know of one, show me the distribution where medians, a difference in medians is the correct way to look at the difference between the distributions. Okay, I'll tell you now. It's the double exponential. Who cares about that distribution, right? So the truth is it's means. You can have different medians, no confounding. You can have equal medians and a lot of confounding. So I have to fight this regularly. And I need the means because that's the only way I can get from a summary measure along with the sample size to what the total is. So table 1, I push for the means. Patient disposition, what happened to them, what was the loss to follow-up, what was the exposure to the treatments, and then in the pre-specified analyses, when we've got time to event data, we're going to look at the Kaplan-Meier, or we're going to look at something called the Aylan-Johansson, a perfectly good measure. People call it, I've adjusted for competing risks. Well, not really. They've sort of adjusted for competing risks. That is to say, it's another state. And as long as the treatment doesn't affect that competing risk, doesn't affect how that would happen, then it's okay. But it does not protect you against the idea that if I cure you of a heart attack, you die of cancer the next day. If there is that association in the data, it doesn't protect you, but it's there. Yes.
So I want to ask you this. So competing risks are almost everywhere.
Yes.
And so how do you deal with this? How do you make it a hypothesis that is cause-specific mortality, but provided that you're not screwing up other causes of death? I mean, how do you actually formalize it? And it's a real challenging cause of interest coming up with estimates that actually.
Yeah. With a bivariate outcome that is the cause-specific and the all-cause. And if you're lucky, they're in the same direction. And so you sleep a little bit easier.
You make a hypothesis on both simultaneously.
And that's what they did here, if you will, that in the cardiovascular death, they treated non-cardiovascular death as a competing risk. They censored those. But then when we later came to all-cause mortality, they were an event. And we did it in the National Lung Screening Trial where we were looking for cancer-specific death. I was on the DSMB for that, and I just said, but you always have to show us the all-cause. And if there's any hint that the all-cause is going the other way, all bets are off. So we got lucky on that one and in spades on this one. What are the descriptive statistics when you're doing a proportional hazards analysis? Lots of times, and I'll show you plenty of cases, the literature will just tell you out of our 8,000 subjects, we had 400 events. That's what they're giving me a proportion. I don't care about that. I want the exponential data. And this is where, I really like proportional hazards model. I had a lot of fun with it, stuff like that. But the fact is the old age and sex and race adjusted incidence rates really get you everywhere. And that's really all you have to do is look within a small enough group. And that's because proportional hazards has been shown to be equivalent to piecewise exponential. And those incidence rates are just the exponential analysis. And if you'll give me the number of events in the person years, I can get my confidence intervals. I can compare across them. I can do everything with it. And I do that regularly with the literature that I had to read, that they tell me about some paper and I go and look at it and say, okay, here I can tell you, over here I can't. You know, they didn't give me what I needed to know. So the baseline characteristics, I just wanted to point out, you know, you give the means, they also give it within each categories, which could matter to us more. What is the mean if you've got a step function? Well, it's binomial proportions is the mean we're interested in there, and we can do that. But, you know, you win some and you lose some. The median high sensitivity C-reactive protein. No, we analyzed this on the log scale. We use geometric means. It's time that the medical world just got used to geometric means, and a lot of them are used to it. But you'll note that on those, yeah, medians were presented. And lipids, I have always analyzed on my t-test on untransformed data. They did want to do it on the log scale. I'm not sure why. You know, I found that unless you're really into the very bad hyperlipidemias, that's how we do it on log scale, but not all this. This is the flow of patients to the trial. It just tells you, you know, who didn't complete the trial, whether they're lost to follow-up, and if they were lost to follow-up, did we know they were alive still? You know, like we could go back, but that means we didn't necessarily know when they had a heart attack, but we knew they were alive. Things like that. And again, it's just going through, and then who did not complete the treatment. And you notice it was sizable by this, an average follow-up of 3.3 years on each arm. 26.7% stopped giving the treatment. 23.6% on placebo. Placebos were having to give themselves shots too. So there. Graphically, you could look at, there was a ramp up in the dose over time. Not surprisingly, the placebo could tolerate every dose level better than the semaglutide group could. Margaret?
So how do you do in a situation like this where there's notorious side effects with keeping them blinding? I mean, if you have a placebo that actually gave the
Because on an individual basis, even if it is a 10-to-1 ratio, there's the one on placebo. So on an individual basis, you can't tell.
I mean, if you start taking this drug and you have GI symptoms that are out of the order, you know which group you're in, right? If you don't have, you don't know.
I have plenty of clinical trials that I look at that's not true. Plenty where, yes, there is an event that is associated as a higher risk on the treatment, but it occurs on both groups. This is a highly morbid population, right? So almost anything you look at, obesity leads to GI problems too. So again, on an individual basis, you aren't unblinded. There are occasionally drugs that turn your urine orange. Yeah.
Question, how often do they collect the data? Do you know which treatment do you think you were assigned to?
Some studies do it. I get nothing from that personally. I mean, you know, they show me that stuff, but you know, and I get even less from the FDA advisory committee meetings where they have people come in and say, and I was on treatment and I would take that again, because what they first learned, you know, was that they were on the treatment and then the company paid for them to come to talk to the FDA. So
that would seem useful, just as quality control or designing future credit, right? If people knew, then you probably should have done the better job with your.
well, yeah, usually what we focus on is trying to keep adherence high. You know, that you'd like them to take it. And so once you start finding out this, well, what can we do to ameliorate that? People that get injection reactions, what should we pre-treat with them with to try to minimize that? Yeah, and we do that on lots of
It's
treatments.
not just that, right? It's also other behaviors. If I know that I'm on Ozempic, I might start eating worse, right? Because I'm taking some other drugs.
Yeah, but now the flip side of that, first of all, if you're on Ozempic, you don't start eating more. By the way, Ozempic and Wegovy have been suggested. Some of this is just on Reddit, but you know, don't want to smoke as much anymore. Don't want to drink as much anymore. You know, I go, does that mean I won't want to sleep as much anymore? Then I won't take it. But you know, but it's been associated with sort of the loss of desire on a lot of these addictive type behaviors. So that's it. But I do all the time worry about the generalizing from a study. And I mean, this is where, again, I'm going to come back to the adherence stuff. With this high lack of adherence, you do wonder that that's what they did when we said, we don't know if this is, prolonging your life. And you never get a chance to tell. I mean, a patient can tell whether they lost weight. They can tell whether their glycemia is getting lower. They can tell whether their headaches are going away. They can't tell whether they're living longer because they took this treatment. So prevention is a scourge there. And so what will happen if I tell you this makes a difference and I know it versus it might make a difference? So that's the flip side that I really worry about is the generalization. This is the cumulative proportion over time. I'm colorblind. For those of you who don't know, I think the top line is blue and the other line is certainly dashed. But the top line is the semaglutide arm. Okay, so now here's the efficacy. So this is the bottom line analysis. A hazard ratio of 0.8. We show this, and now this one is an Aylan-Johansson estimator rather than Kaplan-Meier because we're accounting for the fact that some people will die of non-cardiovascular causes. So it doesn't affect the hazard ratio because we're still comparing the hazard of those at risk, but it will affect the final estimate. Okay, clearly an effect starts very early. Very, very interesting idea. Starts very early that you start seeing those curves separate, and notice that they're separating well at 3 and 4 months before people are up to the maximal dose. Before they're up to the dose that they're going to do. So this was very interesting to us. Before I had access to the data, and I do this for other clinical trials too, do you know that you can just go on your computer and mark out the pixels and look at what the estimates are at each point in time, and then you can try to fit exponential curves to it, see if it fits everywhere? Well, I have an Excel spreadsheet that you can just feed in the pixels and it will do all of that. And I'll tell you, when I do that to this data, it looks exponential. No worry about non-proportional hazards here. Still, you can wonder then, well, if the compliance is that bad later, why is it still proportional hazards if that many people stop taking the drug? And that's an interesting question. This is death from cardiovascular causes. Okay, this was the second in our hierarchy. It comes together. Okay, here's the 1, 2, 3, 4, 5 rule of evaluating any study results. Give 1 hour to 2 people who each have 3 degrees. They will take 4 data points and tell you 5 hypotheses that explain it. Okay, so yes, we all come up with different things that could be going on here. COVID came a little bit into the question. Of course, this is staggered data, but gee, could COVID have been that? So you wonder about that. But because of that, this p-value is 0.07, which means the trial demonstrated that a benefit in MACE. It didn't benefit here, and therefore we can't trust p-values for heart failure or for all-cause mortality. And this is data from, this was displayed in the New England Journal. And the basic rule they have to demonstrate that is you can give us confidence intervals when it's not statistically significant, but you can't give us p-values. And we're not fooling anybody, but that's just the convention. Yeah, some journal articles will make you say, if we didn't give you a p-value, you can't trust the confidence intervals for testing. But what we see here is the confidence interval from 0.71 to 0.96, but it's not statistically significant if you're trying to control the multiplicity. So this is the heart failure endpoint. And this is the death from any causes, hazard ratio 0.81, again, 0.71 to 0.93. And again, it's not there.
So this is interesting. So the confidence interval is not adjusted for multiplicity.
That's correct. It's not. That's right. It's only adjusted if the p-value is there. And the way it's adjusted is not really with joint coverage of the confidence intervals. Instead, it's each one can be interpreted singly, but you've controlled the overall type of error. And this is way better than the things that we used to do. I mean, it's far from perfect, but my point here, yeah, we put it in tables too. And my point here is, rather than, they're giving us the number of events and they're giving us these percentages, but it's percentages over an average of 3.3 years of follow-up. I'd really rather have the rates broken over time. And then this is just, and we have others. And when you look down here, it's not only those first 4, but also we looked at expanded composites and looking at adding in all-cause death instead of CV death and so on as you take it on down there. And it's just things that we look at. What about the support of continuous secondary endpoints? So we're looking at difference in means. It is the mean percentage change in body weight. They don't log transform this to come up with a difference. They instead compute the percentage. It doesn't make a difference in this. But 8.5% average decrease in weight according to this waist circumference and so on. Yes.
So you showed hazard ratio.
Yes.
I'm trying to think, okay, why hazard ratio? And it seems to me that, okay, well, means are problems because of censoring. Medians, you might not get to 50%.
Yeah.
Probabilities, survival probabilities, you need to tell me a point that, so it seems to me that you're really going to hazard ratio just because it's the convenient thing to do. Is it really, something that we can interpret well? Are you convinced of this result?
Yeah, I like to actually, talk about this a whole lot. So, this might be the end of the seminar, you never know. But you look at those two curves and you say they're different. Why are they different? What did you look at immediately and say, gee, they aren't the same curve? And Marco said, well, I can choose 30 months and say the vertical line at 30 months is not beating each other. And I can do it at 30 months, I could do it at 24, I could do it at 104, I can, whatever you want. So we look at the vertical separation, and that is just the difference in binomial proportions estimated using the Kaplan-Meier to at this point. I can look and say, oh, look horizontally, there's horizontal separation. And that can be the difference in medians if we're up high enough, or the difference in any quantile. And there's an infinite number of one of those. We can look at the area between the curves, right? And of course, this is where Levinko can tell you, it's such a nice thing of saying, yeah, looking at weighting the quantiles or weighting the vertical separation, they both get you at the mean. And so the area between the curves is the difference in means, but it doesn't go all the way out. So it's what we call a restricted mean. And there's a paper out, that says, and you can use a little data-driven aspect of choosing when you do the restricted mean over. Okay, how many of you looked at this and said, look, the slope of the top line divided by the y-axis is different from the slope of the bottom line divided by its y-axis. And, well, this is going up instead of down, but that's the hazard, right? The hazard is the slope divided by the probability of being at risk. And so I keep on waiting for somebody to come up with that, telling me that's the difference between these. So, yeah, it's convenience. On the other hand, this is exponential data. And the efficient, and I say it's exponential, it fits. You can't prove it's not exponential.
We didn't know it ahead of time.
But no, we didn't know it ahead of time. But piecewise, you can approximate any curve by a step function, right? That's how we do Lebesgue integration.
Is the natural weighting that you get from using partial likelihood the right kind of weighting of these steps?
Oh, that's real easy to say. Yeah, no, unless you have exponential data, and it's just the right one to use. But when you think about any curve, and look at, we're at 8% here, we're way in the tails. How much is the hazard really changing? How good is an approximation that the hazard would be roughly constant in the tails? It's not a bad approximation. It's which case doing the analysis based on exponential gets the same thing. But no, it's just custom. Where do you put your forks when you set the table? I put it on the left side. Okay, we're just used to looking at that and we can compare it. And then you just have to remember where it can steer you wrong. I can show you data and I do in many things, I can show you data that I promise you, I play Who Wants to Be a Millionaire, and I'll show you curves and I say, is this hazard ratio 2? Is it, I think, what do I use? Do I use 1.3? Is it 0.7 or is it 0.5? That's 1.13 or 1.87. And the answer is stochastically ordered curves that I show you, but the hazard ratio is in the opposite direction. So that's what I can do with proportional hazards. I can't do it in a clinical trial, but I can do it with observational data. So yeah, always be suspect. I do prefer the idea of looking at the restricted mean. Sometimes go to that because attributable risk is more important than a relative risk managerially. And so that looking at the means are there. So I can, so LJ Way, et al. And LJ Way have paper on this. So actually it was Chan at Stanford. So yeah, we're just used to looking at it. That's all. And I'll tell you, it's not steering you wrong in this state. Body weight, mainly showing you this for 2 reasons, right? The one word that I added to our paper on the design and rationale for the SELECT study was they had originally written, we will look at the ability to prevent secondary events through addressing weight. And I changed that word through to while, because it's not at all clear to me that it's the change in weight that we're doing here. It's just while we were giving a weight loss drug, we were changing this. And so here, things that we focused on is the amount of weight loss in the early days when we see an effect on hazard rate. It could be spurious, but we're seeing an effect long before we've lost very much weight. You're talking about a difference of, 5%. So whether you're 100 kilos or 95 kilos, and we don't think that's explanatory for a hazard ratio of 0.8. It could be spurious. But again, this early effect. But the other thing to look at is down at the bottom is the number of participants that we have data on, and we have lots of missing data because people were not coming in for visits, potentially because of COVID, potentially just because they don't do what we told them to do. And so we have lots of missing data as we try to look at weight loss at particular times. I can tell you it's sporadic. Just because you are missing data at 26 weeks doesn't mean you are missing it at 39 weeks. But it is missing. But now what are we going to do as we try to tie these things together? We do subgroup analyses. Okay, this presents all of that data. Just look in this forest plot, a very standard way to look at it. But I want to show you, well, let's see. Oh, well, I'll come back to it. But again, we're looking like by region, for instance, and, what if those are statistically significantly different? We don't give p-values on this one. That suits me fine. How can you tell looking at 2 confidence intervals if you have statistically significant difference between the 2 groups? How many of you learned to look at whether the confidence intervals are overlapping or not? How many of you have learned specifically not to? Okay. Yeah, you don't do that. Okay, now here's a simple rule. If they're independent groups, if the point estimate for one is inside the confidence interval for the other, they aren't statistically significant. If they are not overlapping, they are statistically significant. And all bets are off in the middle. Just do the test. But if is any dependence between the confidence intervals, then all bets are off. Okay, so try to squash anybody who just looks and say they are overlapping and say, do the test. Do the test. And so here's our conclusions. Treatment with once weekly subcutaneous improves MACE, observed early. The early difference between treatment arms suggests that rapid induced effects beyond weight loss may have mediated something else is going on. That's a suggestion, can't prove it. And then we talk about what it has on the markers. Okay, then of course, the proper result of any scientific study is another scientific study. So in some sense, we're done with the scientific study once we've addressed our primary endpoint. You know, I don't think there's anybody in the world that thinks that semaglutide doesn't improve cardiovascular outcome in this patient population. The question is by how much and things like that, but just does that. But now we had pre-specified many secondary manuscripts to do detailed analysis of primary endpoints within subgroups, detailed analysis of secondary endpoints, the joint distribution among the endpoints, looking for both associations or mediation, and then exploratory analyses that were motivated by the trial results. Some of these, there's an element of pre-specification in them, but not perfect, but certainly the impact of COVID-19, the early effects and the adherence. Subgroups, I just wanted to point out, it's very common to give us that p-value over on the right-hand side. The p-value comparing two categories that sometimes there's a justification for and sometimes there isn't. You know, but they give you that p-value, and then the words they most often use is, there were no differences seen between these, or there was a difference, or, you know, whatever. And they would look at this, you know, body weight, 0.1353, and say, no difference in things. Do the most powerful analysis first when you don't know anything. And that's probably a linear trend. Even if it's a step function, the linear trend will capture that better than wrong categorization. And then the p-value, that it just even with that, very low power. Just a rule of thumb, something that I quote to everybody. You're looking for a treatment effect between, you know, treatment and placebo. And 100 patients will give you the power you need. Now, you want to know, does it work in both men and women? And it's 50-50, say. Now you need 230 subjects, 100 in each group, plus you have to penalize yourself for the multiple comparisons. Now you want to say, I know it works differently in men and women. Now you need 400. Okay, we don't go there. You know, long before we discover that we definitely know it works differently, we just say it's expedient to separate them. And the proof of this is, what happens to people's height as they get older? What happens?
It goes up and then down.
Okay.
It goes up and then down.
Thank you. Thank you very much. In my classes, I could just get people to say, you shrink. I said, really? A 3-year-old to 80-year-old is shrinking? No. But how often do we study height versus age, including both 3-year-olds and 80-year-olds in the same days? We never do it. Once it's nonlinear, we separate it out. Once there's an interaction, we separate it out. And so this game over here, just look at the estimates, and it just turns out to be aesthetics. It goes there. Oh, this is all looking at MACE. You know, it's all the news that fits. But this was looking at. I'm sorry, no, this was ETD. This was weight loss. This was weight loss between these different groups. So the estimated treatment difference. Yeah.
So it doesn't change based on weight.
That's right. Yeah. That yeah, it's a very, very interesting aspect there. So what about the joint distribution of these endpoints? Well, why? And I'm just going to use weight loss as an example. Is there an association between weight loss and risk of MACE? Just, you know, is there an association between blood pressure and cholesterol? Just 2 endpoints. Okay. Do the same patients who have weight loss have less MACE? And so is weight loss prognostic for or predictive of less MACE? Okay, predictive means it's tied in with the treatment. Prognostic means it would be working in both groups. Okay, questions that you might want to answer. Does weight loss mediate the improvements in MACE? Is this a mechanism of action for semaglutide? Is this suggestive of future development that we can look for anything that changes weight or not? How do we look at these? Well, I can look at weight loss at a fixed time, or a time average, or anything you want. But the key point is that's a longitudinal measurement versus risk of MACE, which is time to an event. Okay, and what that means is, how do I handle the deaths before the specified time? What about, I can look at the early rate of weight loss versus later risk of MACE. So I can say, let me look at your rate of weight loss during the first 20 weeks, and now take MACE occurring 20 weeks to the end of the study. And there, at least, I'm looking at antecedent risk to subsequent events. But there was differential MACE during the earliest time. So I'm throwing away some of the MACE data as I do that. And of course, I could try time varying weight as a risk factor for MACE. Let me talk about handled deaths before the specified time, because this is as much a question to you as it is telling you what I think. But I can't define this. But what I can define is not your weight loss at 2 years, but I can define your weight loss until the day you die, or 2 years, whichever comes first. Okay, now that's a perfectly good definition, but doesn't mean anything to us. But I can do that. That can be defined for everybody. And then as I try to impute data, I'm just using last observation carried forward. Last measurement I had on you, I'm doing that, and I'm looking at that measure. There is a problem with this, though. If everybody loses weight at the exact same rate, but there's differential survival for other reasons, the group that has shorter survival will necessarily have less weight and will look like an association from that survivorship. There is no solution to this problem that I've discovered, but there are things that you can do to look at the data to say, well, I feel sort of confident with this. But obviously, all of these have drawbacks. The time varying weight as a risk factor for MACE is one that we use for mediation analysis somewhat. I'll talk a little bit more about it. Early weight loss as predictive of MACE. This is that analysis that is 20 rate of weight loss during the first 20 weeks versus MACE afterwards. And, you know, too little for you to see, but allow me to tell you what it is. The group with the highest risk of MACE is the group that lost the most weight while on placebo. The two groups that are pretty coincident are the semaglutide group, no matter how much weight they lost. Now, this is one particular dichotomization of the data, but what this tells you is we're in trouble if we try to talk about weight loss as a mediator, because it's obviously acting very different on placebo. And we're back to the CHS data, cardiovascular health study data, where the people with the highest weight survived better than the people who lost a lot of weight. My father, not long before he died, was talking about how his cholesterol was 119. And me and my sisters were saying, yeah, your liver's not working anymore, is it? You know, I mean, that's, you know, these things that happen just before you die. Well, weight loss just before you die often happens. And so in the placebo group, that weight loss is probably a sign that you're in really bad shape. On the semaglutide group, it's that you're taking semaglutide, which might separately be having benefit through other mechanisms, but it just makes any sort of a mediation analysis on this very, very difficult. But it also tells you that when you're taking semaglutide, if you aren't losing a whole lot of weight, it's okay, keep taking it. You're maybe getting benefit on cardiovascular things. That's what the clinicians want to say. Yes. It's a big deal to them because they're saying, gee, insurance companies tell us, well, we can't give this to you unless you're really obese. Of course, all of these people were obese or overweight. And then the mediation analysis. Is the potential mediator prognostic for the outcome? Does the treatment affect the potential mediator? And how much is the treatment effect attenuated when I adjust for the potential mediator? These are sort of the three litmus tests for mediation. But I will note that in those patients, we haven't necessarily shifted them to a weight that's associated with a lower risk, but the very act of them not continuing to gain weight or this negative energy balance could still be indicative. So weight loss could be a mediator, even if weight itself is not, if you will. But we can explore the time-varying effects as well. We can look at study time, and this is a technical interpretation of the proportional hazards result. We can always do the proportional hazards model, even if we don't have proportional hazards, because under the strong null, which I'm not a fan of, but under the strong null, you do have proportional hazards. But if you don't have proportional hazards, then we're estimating that weighted average of the hazard ratio that Marco minds so much, and I do too. You know. Early effects might be suggestive of alternative mechanisms of action, and then you also might want to look at the possibility of tachyphylaxis, that the treatment effect wears off. And I use words like this that you never heard of. In my introductory classes, I used heteroskedasticity when for the same syllables, I could say variance aren't equal. But, you know, it's the point of people saying, no, this was an important concept that we need to have a word for. And then calendar time, are there secular trends in patient accrual? What about the COVID-19? How? We could look at longitudinal graphs of the continuous measures or weight and so on. We could look at cumulative estimates of hazard at each point in time, or we could look at interval estimates of hazards. Yes.
You have a graph for weights all the time.
What?
You have the graphic separation of weights.
Yeah.
There. And so, you look at that graph and you sort of want to interpret temporal trajectory and interpret at the individual level. But as you showed at the bottom, we're talking about different subset of individuals.
Yeah.
So what do you do with that?
So the most you can do is you can look at the individual trajectories and say how many patients stay there. But of course, then a major issue is, and if they stop taking the drug, did their individual weight go up and how soon afterwards and so on? It's much more complicated analysis. It's so much easier to find a population of identical quadruplets and talk about that population exactly than it is to talk about any one of them. And so that's the thing. But no, that's a very big concern. If you look at height curves, back to height by age, it looks like it goes up and then it levels off. But if you look at it for each individual, it has a big jump and cuts across there. So the population average of height over age looks very different from the individual curves. So this is from the literature, not from this study, but it is for dapagliflozin of another diabetes drug. And what they gave was they gave an estimate of the hazard ratio as computed to every point in time. So they just censored everybody at successive times and looked at it. I don't care about this curve at all. Okay, because what are my questions? My questions are how are the hazards changing over time? And looking at this cumulative effect is obscuring that. You know, is that lower hazard ratio, is that just spurious random variation and it's finally settling down on the truth? Or is it really that there is a better hazard ratio early on, perhaps because compliance is still high, perhaps because the mechanism you're doing only has short-term effects, who knows? But as you then average it out, I can't tell anything there. I can't see what's happening. I can try to infer it, but the true sin on this graph is in the third panel, or the second panel on the top. Second panel at the top. So what is the sin that's done there? It's statistical crimes against humanity. They're telling us the first time they had statistical significance. Can you give me a confidence interval for that? There is no variability on that. You're talking about something that is all related to how we did the study. It may tell you a whole lot about me and how I did the study. It tells you nothing about the science. But clinicians will say, when did it become statistically significant? I go, significant testing what? You know, so I very much object to them giving me that, particularly rather than the breakdown over time. But you see, I spend a lot of my time. I tell people that yes, I'm a closet Bayesian and I'm a incoherent one at that. It's the most important thing to look at, but I don't keep the same prior as I learn more. I do different things, but frequentist is what's reproducible. You know, that I can tell you what I've done. Impact of COVID-19. This is from a paper from the select data. They looked at the top panels are CV death, non-CV death, and death from infectious causes. I don't, again, a lot of this is adjudication. I don't really trust that. You know, when you die from cancer, what do you die from? how does cancer kill you? One of my favorite on breast cancer oncology was when I posed this question when I was trying to say I don't trust this call specific stuff. She says, cardiopulmonary arrest. All of my patients die of cardiopulmonary arrest. You know, and that is the problem. So infectious causes, you can look at somebody in sepsis and say they died from liver failure as part of the sepsis, or you could say it was an infection, or it could be that it wasn't an infection at all. It was instead a necrotic organ that's causing problems. You know, so okay, that having been said, we see the graphs of the cumulative incidence curves, and then over here we see how the rates are changing over time, and they tried to draw lines around the time that the pandemic was at its height. So, you know, it looks, you know, suggestive that the treatment was actually beneficial if you had COVID. So, no proof. And now we come to the adherence trial. You know, patients who don't follow the protocol may be irrelevant to what I want to estimate. You know, I don't want to know what happens when I randomize you. I want to know when you take the drug. And yes, I do want to know that. It just may not be answerable rigorously. There's patients who don't follow directions. There are patients who have intolerable adverse reactions, but maybe they're intolerable only because they are uncertain of the efficacy. But perhaps that headache that you have, if I make you keep taking it, it'll turn into a cerebral bleed and you'll die. You know, we don't know. Patients with real or perceived lack of efficacy. We can have development of a contraindication to treatment like pregnancy, patients with early evidence of cure, and patients with competing risk that prevents measurement. And, you know, what should you do? This is a word of caution, and many of you have seen this before. And in my steering committee meetings, I show it to any number of people any number of times. But this is protopathic bias. Here was a case in a diabetes clinical trial that it was a cardiovascular outcome trial. This was exenatide. So it was that Excel trial that I talked about. They did not prove superiority with respect to MACE. And they weren't happy about that. And so let's go through and reanalyze our data because lots of patients changed what they were taking in terms of drugs. So they took open label drop-in of other glucose lowering medications. The pragmatic trial allowed people to change it as ever they needed to. Placebo arm had more such modifications. There were some GLP-1RAs and SGLT2s are another drug, both of which were known to provide MACE benefits. And, you know, they say, with these being used, there's greater likelihood that their open label drop-in could impact clinical trial event rates. Yeah, true. So we used several statistical techniques. Actually, I think they used one statistical technique twice, but they thought it was several. I could do, and so this is why I campaigned so much, they didn't give me the average time of follow-up on this trial, and they didn't give me per events. They gave me the medians. And so I had to just live with that. And I used, you know, I just said, lacking anything else, I can do this analysis. And so they gave me in their follow-on paper, I had what the difference was overall time. And they gave me in this follow-on paper prior to changing the therapies, I could come up with that. And I know how to subtract as well as the next person. So I could compute the difference of other people after the censoring time, what was happening to the patients when they changed their therapy, then what was their risk. And I could reproduce, by using the median, I could reproduce their data to 2 significant digits fairly well. So I feel fairly comfortable about this. So what do we have here? Well, if I just look at the placebo group who is changing therapy, they are adding on additional glucose lowering medications. You would think that would be a good thing to do. But on the other hand, the fact that they needed to is a bad thing. So which held sway? Is it more that it was a bad thing that they needed to, or was it a good thing that they didn't? And as I look at the hazard ratio, that's actually incidence rate ratio, the incidence rate ratio for after they changed their therapy, it's always higher for no matter how they were changing that therapy. Always higher. The most interesting thing in all of this is the GLP-1 RAs. They were on blinded GLP-1 RA therapy, but some people stopped taking it and then started taking a GLP-1 RA. On the exenatide arm, the hazard ratio, not super precise, but it's there, is 10. They had a 10-fold higher risk of events after they shifted from, and a lot of them did shift to exenatide, from exenatide to exenatide, not all of them. 10-fold higher risk, right? On the placebo arm, it was only a 7-fold higher risk. Why would people change their therapy? They weren't doing well, right? And the more you bring the high-powered drugs, probably the more they weren't doing well. And so the premise that we're looking for their cardiovascular disease to get worse, but then we want to penalize them if their diabetes is getting worse, makes no sense. Of course their disease progresses. Of course we have to modify their therapy. And that's why you have to do an ITT analysis. Okay. Now, that having been said, I'm very interested in doing adherence-based analysis here, but I've got to keep this in mind. It could be this protopathic bias. Things were happening that were indicative of an impending change in medical status. So what's the differential diagnosis? Well, I do have to worry about changing hazard. It's possible that the hazard was just increasing over time, and I didn't have that. But to the best of my ability, it looked exponential. Could be toxicity of those added drugs, but they're all approved, widespread use. Could be rebound. I do have to worry about rebound with some diseases that at baseline, so some of the asthma drugs and stuff, you take the asthma drug, you're better. You stop taking the asthma drug, you're worse than you were at the beginning. So that rebound could be confounding. And then, protopathic and or indication bias. They stopped taking it and changed to other ones precisely because they were about to have an event. The last thing I want to do is just talk about something that's clearly not my job, but it is just the point of talking to the importance of all of these trials. I talked about how the United States has the worst obesity of Europe and North America. Here is what is being charged for these drugs. A 1-month supply. We're paying for this. The United States is paying for this. Novo Nordisk, as this is the largest company in Europe right now. And its valuation is more than the annual gross domestic product of Denmark. So it's there. Now, on the other hand, the clinical trial I was just talking about cost $1 billion to do, in addition to all the other ones. So what is the cost of finding all of this out? And, what do they do? And, why, if you, that's not true anymore, but why could you get cheaper airline tickets if you book 2 weeks in advance? And who was subsidizing who? And the answer was, well, business was doing everything and they could sell those extra seats. And it was gravy for them. Why do you get the junk mail you do? Well, because that whatever money they do, they're going to come to your house anyway. They can charge less for that. And so it's an economic thing, but I think you'll continue to see this is it's a major public health problem, is obesity. It's going to cost us a lot. And so that was just my.
That's why Novo Nordisk wants FDA approval.
Yes. Yes.
Are they paying you proportionally for your participation?
As I said, I am not being paid for any of these papers that I'm working on, and I hear about that regularly from my wife. And saying, you're retired. But it is this thing that you have to, I rail against accelerated approval in cancer. Absolutely, that is just the worst possible thing, that they're letting drugs that just don't work, that never get approved in Europe. They've been approved here, that they can't ever be confirmed. But can I prove that putting that profit motive didn't lead to a lot of companies with the great advances that have been made recently? I can't prove it. I don't like it. I'd rather have a rigorous thing, but I can't prove that there isn't such a profit motive, that people are stumbling onto the good things because of it. And so you just have to consider that. And again, it's not my job. I don't have to do this, but you got to start thinking about what's the number needed to treat. The number needed to treat over 3.3 years to prevent 1 case of MACE Well, there was a 1.5% difference. You're talking about you got to treat 60 people to prevent one case. So you have to think about those things. And, you better believe people are doing these analyses and people who know more about it than me. On the other hand, anybody who's ever seen one of my seminars knows the seminar's not over until they see this curve, this slide. And this is because this is the most famous of all statisticians ever. And the answer is you just have to think about what you're trying to do. And really, even the simplest of statistics that you learn in your first class regularly get misused if you don't really think about what question you're trying to answer. Okay, thanks. I'm so far over that, I apologize for that, but. But
Someone raising hand.
yeah, I don't, let me see where the chat, here's the chat. Yeah, okay.
When people should leave, if you need to leave.
Yeah.
Great presentation, Scott. I'd say we need you for 30 hours in Biostat 524 to go through all the issues in depth. A lot of them deserve a lot of questions. There's just one that I want to touch on.
Yeah.
And that is, I love your point about the clinical relevance of the mean.
Yes.
And I fight that all the time. I know in age-related macular degeneration, people are saying BCVA, you need to see a 15-letter loss for failure. Nonsense. It's every 10-letter shift in the distribution matters to patients.
Yes.
Unless you can tell me that represents that when I'm in Seattle and it rains at nighttime, I can't drive. Okay, that's dichotomous.
Yeah.
But so the issue I wanted to raise, and I think you know this well, is in multiple myeloma, where major progress has been made in recent years with CAR T cells. And to deliver CAR T cells, it takes 3 or 4 months you randomize, takes 3 or 4 months to produce. Those survival curves tend to come down in the wrong direction. Then you give CAR T and they splay out beautifully. And people say, oh, well, we can't use proportional hazards, even though it's the weighted average time-varying hazard ratio. Let's use the mean, but we'll use the restricted mean. So we'll truncate the data at 2.5 years because that's not basically vulnerable to non-proportional hazards.
Yeah.
Well, wait a minute. If it's non-proportional hazards, the mean that you're throwing out, which is the area between the curves after 2.5 years, is incredibly important, and in fact will be even more beautifully separated.
Yes.
So to solve the problem, I think LJ is among those arguing.
Yes.
So we can't use proportional hazards if it's a time-varying hazard ratio. So we'll use restricted mean when absolutely that restricted mean at 2.5 years doesn't represent the area between the curves.
Yeah.
It's beautifully splayed out later.
Yeah.
And by the way, one other thing is don't cross over at the time of progression as ida-cel did compared to cell because you'll miss the effect.
So you bring up the LJ way, and I was looking through again a referee's report. I sent to him on that and was just laying out all of these things and recognizing that they were so quick to say, the mean, if you catch that, I said, but it's not necessarily more powerful because as you're estimating the distance between two curves, as your Kaplan-Meier curve becomes more variable, you can actually lose power.
Yes, you can.
As by taking it out too far. So it's a very hard thing to do. And I never know how much I want to just look in the very tail of the curve and say, this is the best thing. And in childhood cancer, we don't. In childhood cancer, you don't want to do a 4-year study. You want to do a 10-year study minimum, because that's what matters. But for somebody my age, I go to the doctor and say, you only have a short time to live. And how much is it? It says 10. I say, well, 10 months, 10 years, 9, and so, it's this idea of how long it is. And you have to take those into adjustment. So I'll send you, if you'd like to see my full treatise that I gave them on that, where I laid out these different curves and what proportional hazards would say and what the difference in means would say and what they say. And this is the answer. You have to say, what do we care about here? And why I get away with saying it's the mean we care about, because the geometric mean is the mean of the logs. The proportion is the mean of a binary. The rate is the mean of events divided by that. They're all means. It's just that looking at that knee-jerk reaction to convert into medians, and back to the medians, we know that if I have complete data, we have no power to detect the median. You know, that the median is just a far more variable thing to estimate than means if they're answering the same question.
If they're answering the same question, they're not.
Pardon?
If they're answering the same question, they're not, they're different. estimates.
Yes,
So-
and so is it more important? Is it more, this is an interesting question, though. Where we do tend to use medians a lot is in the social importance of wealth, for instance. You know, they'll talk about what is the median wealth of King County versus what's the mean wealth. And sometimes when you're talking about the economic force in King County, I'd far rather have the means. You know, the billionaires who live here contribute to it. And when you want to talk about how happy I am, the median might, might be a better thing, but just know what it is that you're trying to estimate. And even better than the median is the proportion of people who earn less than $100 million a year, you know.
But you do not be guided necessarily by power issues, right? First,
No.
scientific question.
First, yeah, so I bastardized something that Tom said about choosing your clinical endpoint. First, choose what's clinically important, you know, heart attack or not. Then choose what's plausible. Are you going to affect a heart attack or not? And then choose what you can estimate precisely. But the same is true about the summary measure. First, choose what is clinically important, then choose what's plausible, and lastly, go for statistical power. And it's rare that they're all, you know, that it comes down to that. Instead, get the most statistical power with the summary measure of the clinical outcome that matters.
That's right, and patients care about survival. And if patients only care about their early survival, fine, use the median. But immuno-oncology agents, they are fantastic. Immuno-oncology agents can take the last third of that distribution and extend your survival forever. Your median show no effect.
Well, I used to give my classes in 517, I gave them a data set and said, you're an unethical researcher. You're allowed to change one number to get your treatment to look better. You can choose one number. What number will you change to get the mean to look better? And what one will you change to get the geometric mean to look better? And there was no number you could change to get the median to look better. Well, good news or bad news? It's good news if you're really worried about an unethical researcher that's only allowed to change one number. But in cancer, for instance, we know that cancer is an outlier. Even when you die of overwhelming cancer, the majority of your cells in your body are A-OK, you know? And so we're looking for that outlier. We're looking for that. And so detecting that with the mean, when you don't know where to draw a line for a proportion or anything like that, the mean is an omnibus test that is better at catching all sorts of things than the median. And
It seems that this is because we really feel the need to have a parsimonious summary. I would say I want neither the mean nor the median, show me the curves. Show me the entire curve.
oh, well, I can show you the entire curve, but we still have to summarize it some way.
Yeah. And
Yes.
account for the variability in the right end.
Yeah, we have to because the multiple comparison problem, again, you can't give me that time of the earliest significant p-value. You can't give me any inference, and that's an infinite number of analyses you're doing. Well, you know, in sequential analysis, if you just do a sequential analysis, collecting your data, and the truth is the null, with probability 1, you will eventually find a significant value. Probability 1. Now, how do you control for that? And so there's lots, you know, I'm the first to dump on frequentist inference, but used wisely, it's reproducible. Bayesian inference is, you know, is the vague answer to the right question, and frequentist is the precise answer to the wrong question, except in a designed experiment. And in a designed experiment, it just so happens that I come prepared. I come prepared, but, you know, this is a simplistic world, a binary decision space, binary data space, but the posterior odds is the Bayes factor times the prior odds. Everybody can walk in with their own prior odds.
Yes.
And if I tell them the power divided by the type 1 error, they can come up with their answer.
Yes.
So, I mean, that's the thing. So there's no question. But here's the other proof that I have for this is How many of you have ever had a diagnostic test used on you? You know, like a thermometer, say, right? Now, when they quantify a new diagnostic test, when there is absolutely zero question that in practice it's the positive predictive value we care about, but when they discover a new test, what they characterize is the sensitivity and specificity. And that's because every doctor has a different prevalence. And so that they have to learn what to do with that prevalence, but boiling it down to the positive predictive value will not be useful to everybody. You know, somebody who comes in with a positive VDRL in a sexually transmitted disease clinic, they have symptoms. Somebody who comes in with a positive VDRL and pediatric, you know, yeah, do they have an autoimmune disease? You know, I mean, that's the things that you have to worry about. So the same things holds here. So
Well, I have one last question, perhaps.
yes,
Aren't you having fun here?
I do.
You should probably come more often.
I like-
Are you committed to coming more often?
I like to come to seminars. It was always an important thing to do because what I lack in knowledge, I make up for opinions, and the best thing to do with opinions is to spread them around to other
And we
people
miss
who
your
have
opinion,
them.
so please come more often.
And having been to many seminars with Scott where he's attending, I've never been to one where he didn't ask a probing question.
I agree. I'm encouraged. We miss you. Yeah.
So, well, I appreciate your stamina staying here. I couldn't have taken names as you walked out. So, so, well, I do appreciate the chance to do it. So I welcome the fact that you were asking for people.
It's,
Yep.
this is great.